Welcome to part 2 of the tutorial on equivalence class testing. In this tutorial, we're going to think about equivalence class testing when we know the purpose of the method that we're testing. Of course, this is a much more common situation than we had in the artificial situation that I described in part 1 of the tutorials. However, in that first part, we at least introduced equivalence classes, and you now know that the idea is to divide the input space into a set of equivalence classes with the property that if we can test one element out of each equivalence class, we can very quickly test the program. And if when we test something from an equivalence class, if that data element works correctly, then it's likely that every other element in that equivalence class would produce correct answers. And conversely, if that element, when we test it, produces a failure, other elements in that equivalence class would also cause a failure. Now, creating an equivalence classes with those properties is not easy, but it is easier if we know the purpose of the method. I want to start with an example. It's a similar example to what we did in part 1. However, in this case, I'm going to tell you the purpose of the method. The purpose of the method is to determine whether a person is eligible to vote and whether the person is eligible to drive a vehicle, given one input, which is the age of that individual. Let me illustrate the situation. Suppose that the age is less than 16. Then the method should report that that person is too young to drive and too young to vote. However, if the person's age is 16 or greater and less than 18, the method should then report that the person is eligible to drive but not eligible to vote. And lastly, if the person's age is over 18, then that person is both eligible to drive and to vote. All right, given that information, what equivalence classes do you think there should be? Let me pause for a minute and let you think about that. I hope that you thought about the ones I'm going to describe here. Let's let this oval represent the entire input space for the integer parameter age. And I suspect you came up with the class age less than 16, another class for age between 16 and less than 18, and a third class for those with age 18 and older. And that seems reasonable. Is this any better? Notice in this case, I use the fact that human age is never a negative number, so why should we include that? Let's exclude that age. And so the first class is age greater than or equal to 0 and less than 16. The other two classes are the same. Is that an improvement? Well, from a logical point of view, it seems like that would be the right thing to do. However, let me ask this question. If you were testing that method, would you be surprised if someone incorrectly put in a negative age? Of course, no one has a negative age, but there's nothing in the method that prevents people from passing in a negative age. So we ought to at least test that, and in that case, the program should fail gracefully. That is, it shouldn't cause the program to crash, but should give a nice error message and ask the person perhaps to re-input the age. So perhaps it's better to capture that with a fourth class. This clearly is an error class, but it is something that we ought to test for. Now, with that, we have a complete set of equivalence classes. The term complete here is important because any set of equivalence classes needs to be complete by which we mean it covers the entire input space. There's no possible age that you can enter on the computer as an integer that's not covered in one of these four classes. Let's consider another way of stating that same set of equivalence classes. Now you'll notice the difference here is that I've replaced the less than symbol with less than or equal. Now the problem with this is that the equivalence classes then have an overlap. The age 0 is in two categories, and the age 16 is in two categories, and the age 18 is in two categories. Of course, that's not what we wanted in this case, but I just wanted to make it clear that that's a situation to avoid. It is complete, but is it independent? That is, are the classes independent? And the answer is no, they are not. They are overlapping. Any set of equivalence classes needs to have two properties. One, that they are complete, and again by that we mean they cover the entire input space. And secondly, that they're independent, that there's no overlap. There's no one point that's in two equivalence classes. Well, here's the final version that I've decided to use. Now you'll notice here that I've added another equivalence class at the high end. And that's using some other knowledge of human age, some other knowledge of the function of this program. The age clearly cannot be 200. There are no humans that are age 200. Now the only problem here is what should I include as the top age? I recently heard of a person who was, I believe, 115 years old, and I think there have been some approaching 120. Well, I arbitrarily picked 120. The real answer for this is we should go back to the person who is asking us to create this method, that is the specifier of the program, and ask them what's the appropriate top end for ages. But we'll go with 120 for now. Now, what do we do with this? How do we test with this? Well, test cases, one from each. So for example, for negatives, I've picked -3. For the second category where they can't drive, I've picked the age 10. 17 is those that can drive but cannot vote. 29 to represent those that can drive and vote. And 150 for another error case for those that are too large. Are these the only possible things I could test? No, remember the principles behind equivalence class testing. We can pick any element of the class and test from it, and that should be representative of all. So at this point, go to take the quiz and then go on to part 3.